Acid-base and gas evolution reactions. We talked about precipitation reactions. Two other classes of reactions can occur when you've got the anion from one reactant combining with the cation from the other. In an acid-base reaction, which is also called neutralization, you have an acid reacting with a base. See how the name gives us a clue? We got real creative with these names, right? An acid and a base, and they neutralize each other. And when an acid and base combine, they produce water. Sometimes they'll produce a weak electrolyte, but generally one of the products is going to be water. And a gas evolution reaction evolves a gas. We usually see this as bubbling or fizzing. So we don't talk a lot about acids in Chem 1A. That's more of a Chem 1B topic. So this is just a little overview. One of the definitions of acids and bases is the Arrhenius definition, and this is named after the Swedish scientist who came up with it. An acid is a substance that produces hydrogen ions in aqueous solution. So HCl, AQ, we've learned to name that as an acid, right? This is hydrochloric acid. It dissociates to form hydrogen ions and chloride ions. Now, the hydrogen ion, let's think, what is a hydrogen atom? How many protons and electrons does a hydrogen atom have? The atomic number is 1, right? Atomic number 1 means 1 proton and then 1 electron. So if we have a hydrogen ion, a cation, that means it lost its electron and all that's left is a proton. Just a bare proton floating around. It doesn't actually float around by itself. What happens is this proton, this hydrogen ion, is actually donated to a water molecule and forms the hydronium ion. And here's a picture of a hydronium ion. It's a water molecule with an extra hydrogen ion, so it's got a plus charge, H3O plus. And we could write it as an equation like this, H plus plus H2O gives this hydronium ion. Now, it gets a little tedious to always write out the hydronium ion in equations, and so often we'll just show H plus. But a chemist understands that you can't have hydrogen ions by themselves. In chemistry land, I think of them as being infants, like a 3-month-old baby. You're not going to see a 3-month-old baby wandering around Disneyland by himself, right? They're too small. They're always going to be carried. There are 3-month-old babies at Disneyland, but they're in a stroller or mom or dad are carrying them around. And that's what the hydrogen ion is like. And so then the water molecule is like the mom or the dad or the babysitter. So it's always being carried around. So try to keep that in the back of your head. And then what's a base? A base is a substance that produces hydroxide ions in aqueous solution. So if we look at things like sodium hydroxide, which is an ionic compound that's soluble in water, it's very easy to see how this produces hydroxide ions. It just dissociates into its ions, sodium ion and hydroxide ion. But then there are other bases, such as ammonia. Ammonia is a base, but it doesn't have hydroxide ions in the molecule, so then what does it do? It produces hydroxide ions by pulling hydrogen off of water molecules. Should really be a place where that's kind of shown. I don't know where I'm going to write that. I'll try to squeeze it in up here. So NH3 plus H2O. What's going to happen is that the ammonia is going to pull a hydrogen ion off of water, and you're going to get NH4 plus and OH minus. And that is how ammonia is a base. It produces hydroxide ions in solution, even though it doesn't contain any hydroxide ions itself. Polyprotic acids. Polyprotic means multiple protons, many protons. So these are acids that release more than one ionizable proton. So sulfuric acid, H2SO4. It has 2 hydrogen ions that can be released. H2SO4 is considered a strong acid, but it doesn't release both of its hydrogens right away. So if we're going to be complete about this, we'll write plus water, and this will go to HSO4 minus plus H3O plus. That's the first proton being released. So one proton is released and goes on to the water molecule. That's what makes it an acid. And I wrote this as a single arrow because this goes pretty much completely. That's the strong acid. It says it's weak in its second. So then this also acts as an acid, but this is a weak acid, and so it can release this hydrogen ion, but it only does so to a small extent. But it can release 2 protons. And there are bases that can produce 2 moles of hydroxide ion per mole of base. Can you think of a base that might do that? How about something like magnesium hydroxide? Each mole or formula unit of magnesium hydroxide has 2 hydroxides. So it can release 2 hydroxides for each unit of this. Does that make sense? We don't have a name for those. We have a name for the polyprotic acids. There's a monoprotic acid has 1 proton, diprotic has 2, and a triprotic has 3. So what happens in these neutralization reactions is that the hydrogen ion that gets released from the acid combines with the hydroxide ion released from the base, and that makes water. And then the cation that's left over from the base, the anion left from the acid, combine to make a salt. Now, when a chemist says salt, it's not always sodium chloride. Salt is a generic term for an ionic compound. So any ionic compound is technically salt. So here we have the acid, HCl, plus the base, sodium hydroxide. This hydrogen and the hydroxide ion are going to combine to make water. You can look at this equation down here. H plus OH minus gives us H2O. Now we're writing H plus even though we understand that hydrogen ion is writing piggyback on a water molecule. It's just simpler not to draw all that out. And then so then what's left? Well, the sodium ion and the chloride ion. And so when you mix the correct amounts of hydrochloric acid and sodium hydroxide, you get salty water. And so the net ionic equation for acid-base reactions is generally going to be H plus OH minus to yield water, unless you get an insoluble salt that forms, which is not typical. Yes?
When you do this reaction, since you can't see it, it just produces heat, right?
Yeah, when this reaction like this occurs, there's really nothing that you can see happening. Generally, there is a little bit of heat observed. You'll notice that the solution gets warm. If it's real dilute, though, you might not even notice that. But we'll see in a minute what we do to make it visible. Any other questions? There's a picture. Putting aqueous hydrochloric acid where we've got these hydronium ions and chloride ions. So the H plus from the HCl is riding on the water. And then here we've got sodium hydroxide with sodium ions and hydroxide ions. And the sodium ions and the chloride ions just end up floating around. They didn't participate in the reaction. But the hydronium ion loses one of its protons. The little proton that's riding piggyback will go over here and make a complete water molecule. Here are some common acids and bases. 1, 2, yeah, these are the strong acids, which, you know, I don't know how I missed that, but these are the strong acids right here. So these are strong acids. When these guys dissolve, when they are in aqueous solution, they ionize completely. And again, we mentioned that sulfuric acid is diprotic, but only the first hydrogen comes off completely. And then two common weak acids are acetic acid and hydrofluoric acid. Now, students often ask, well, why is acetic acid written as HC2H3O2? Shouldn't it be H4C2O2? Or put all the hydrogens together in one place or another? We write it this way because only one of those hydrogens is ionizable. Acetic acid only loses one hydrogen when it is dissolved in water. And so we write that hydrogen first. These hydrogens stick together. They stay part of the acetate molecule. And so hydrofluoric is another weak acid. Here are some common bases. Most of the hydroxides are not very soluble. But sodium, lithium, potassium hydroxide, and then calcium and barium hydroxides. These are considered strong bases. They'll ionize completely. Ammonia is a weak base. And here's the equation down here, like I drew earlier. It doesn't have OH in its formula, and yet it does form hydroxide ions in solution. So let's practice here. Let's write a molecular and a net ionic equation for the reactions that occur between aqueous H2SO4 and aqueous LiOH, lithium hydroxide. That's supposed to be a subscript. Not a plus, it's a 4. Okay, so first thing is we have to write down the reactants. H2SO4, and that's going to be aqueous because it says so. And lithium hydroxide is aqueous. Now, we can do the same thing that we did with the, with the precipitation reactions, and look at the ions that form. So lithium hydroxide is obviously an ionic compound, and that's going to have lithium ions and hydroxide ions. And the acids also form ions in solution. And so this will ultimately ionize to H plus and SO4 2 minus. This one's a little bit sticky because it's a strong acid in its first hydrogen and a weak acid in its second hydrogen. We're not going to worry about that. It's the only one that's like that, so we're not going to worry about it. We're just going to assume, since it's with a strong base, that it's going to eventually ionize completely, be completely neutralized. And then we can think of this in the same way as we thought of the precipitation reaction, of what happens if we swap the partners. So hydrogen ion and sulfate ion came to a party together. Lithium ion and hydroxide ion came to a party together. They're mingling around. Let's see if anybody hits it off, right? So over here, we'll get lithium with sulfate and H plus with OH minus. Well, is lithium sulfate going to be soluble or insoluble? Soluble. All of the alkali metals, lithium, sodium, potassium, any of their compounds are always soluble. So that's going to be aqueous. What about H plus and OH minus? If we just push those together, we get HOH, and hopefully we recognize that that looks a little weird. Oh, wait, that's H2O. Is H2O aqueous? How can water be dissolved in water, right? Water's a liquid. So H2O is a liquid. If you form a liquid, a solid, or a gas, you have a reaction because something new has formed. So even though we don't have a solid forming, we do have a chemical reaction. And then this would be Li2SO4 aqueous. So we've got, it looks like Liz, we've got our products now. We need to balance the equation. Is it balanced as it is? No. Over here we've got 2 hydrogen ions, and here's a hydroxide. Over here we've got 2 hydrogen ions and an oxygen, and we look at that and we're like, that's kind of hard to think about. Let's start somewhere else. Let's start with this guy, lithium. There's 1 here and 2 there. So if I put a 2 in front of lithium hydroxide, that fixes the lithiums. Those hydrogens and oxygens were being obnoxious, so I'm going to avoid them. Here's SO4, and here's SO4. I know there's oxygens other places, but here's the SO4, and there's the SO4. It didn't come apart, it stayed intact, so that's okay. Now, we have to deal with these guys. So there were 2 of these and 2 of those, and how many water molecules is that going to make? 2. So we need a 2 over here. It's not the only way to balance that equation, and probably wasn't the best way, but that's the molecular equation. Any questions about that? What you'll find is if you have a diprotic acid, you'll end up with 2 water molecules. If you have a triprotic acid, you'll end up with 3 water molecules. Now we're supposed to write the net ionic equation. Well, here I already have my ions written out. So what we need to do is we need to figure out which ions are not involved in a change. So there's a couple of different ways to approach this. Since this is, we're still in this chapter about net ionic equations and everything, I'm going to just sketch out the total ionic equation or the complete ionic equation. From this, I'm going to get 2 H pluses and an SO4 2 minus. And then I'm going to get 2 lithiums and 2 hydroxides. And then over here, I'm going to have 2 lithium ions and a sulfate. And then would I separate water into ions? No, because of its state symbol, it's a liquid. Only aqueous things, and then only strong acids. I'm separating this one because it's a strong acid. Plus, got to keep the numbers, 2H2O. Now we can see that the sulfates didn't change, and the lithiums didn't change. And what I've got left here is 2H plus 2 OH minus going to 2 H2O. And I can divide everything by 2, and then I come up with hydrogen ion aqueous plus hydroxide ion aqueous forming water. And that's my net ionic equation. Any questions? Yes?
With the 2H plus,
Mm-hmm.
why is there 2?
Good question. Why is there a 2 here? Because this is H2, SO4. So when this comes apart, there are 2 hydrogen ions.
Okay, so that still carries over even though it's the charge from the SO4?
Well,
Like when you do the ionic, because I didn't do that on the worksheet, that's why I was wondering.
okay.
Usually if like the 2's in front, then...
The 2 in front means there's 2 of these H plus ions. If we keep the subscript, then we're doing we're looking at like a molecule of hydrogen, which is not the case here. This is 2 hydrogen ions. Maybe it's easier to think of in looking at the lithium sulfate. The lithium sulfate, the sulfate has a 2- charge, the lithium has a +1 charge, and so there are 2 of these for every one of those. I don't put coefficients down here because it clutters things up. These are my notes. They're not actually writing an equation. If you don't want to just carry numbers down like that, you can just write the ions without any coefficients and then balance the equation when you're done. That's another option. And it just depends on what makes the most sense to you.
That's what I didn't do.
You didn't balance it? That won't be a big, big problem. Okay. Okay. Acid-base titrations. Have you guys done titrations before? Yeah, you should have, but that doesn't always mean you have. Okay, so a titration is just a technique. And we take a substance in a solution where we know the concentration, and we react it with another substance whose concentration we don't know, and then we can use that reaction to figure out that unknown concentration. So we're going to take these 2 solutions and add them together until we get a stoichiometric ratio. We talked about limiting reactants and how usually there's an excess of one of the reactants. The stoichiometric ratio is where we get just the right amount of both of the reactants. And that's the ratio given by the stoichiometry of the equation. We call that the equivalence point. And we can use the amount of solution added and the concentrations to figure out that unknown concentration. That did not go very well. Now, as we mentioned earlier, when you have an acid-base reaction, there's nothing to see. There's some heat generated, but that's not going to help you identify where that equivalence point is. And so what we often do is we add an indicator. An indicator is a substance that changes color depending on what the acidity level of the solution is. And so then we get a visual clue that we've gotten to the equivalence point. At the equivalence point for acid-base reactions, the moles of hydrogen ions are equal to the moles of hydroxide ions. So you have just the right amount. And when we get that color change, we know we've gotten there. Here's a picture. Illustration, really. So we know what this is, right? This is a burette. And burettes are useful for adding and measuring volumes of liquids. And so here we have a hydroxide solution in the burette, and down here we have an acid solution. So we add the hydroxide ion to this solution, and as the hydroxide ions are added, they will neutralize the hydrogen ions that are present in the acid. When we get to the equivalence point, we've neutralized all of the hydrogen ions. There aren't any left, and that causes a shift in the acidity of the solution and causes the indicator to change color. And we see that color shift, and we know to stop. These are actual photographs. It's clear, and you add, and after a while, you start to see a little pinkness here, but then when you swirl it, when you mix it up, it goes away. It's just a little bit pink here because where the sodium hydroxide, or this is sodium hydroxide, where the sodium hydroxide is being added, it hasn't mixed yet, and so here there's a little bit of excess of hydroxide, but when we mix it around, there's plenty of hydrogen ions to neutralize that. And when we get one drop past the equivalence point, just a teeny tiny bit past, the whole solution will turn pink. So let's do an acid-base titration calculation. These are just stoichiometry calculations. So a titration of a 20 ml sample of a sulfuric acid solution of unknown concentration requires 22.87 milliliters of a 0.158 molar potassium hydroxide solution to reach the equivalence point. What is the concentration of the unknown sulfuric acid solution? So that might seem like a lot at first. Let's just break it down. This is a stoichiometry calculation, and so we need a balanced chemical equation. So we've got sulfuric acid reacting with potassium hydroxide. So H2SO4, and we can skip the state symbols here because the goal of this is not to write out chemical equations, it's to figure out concentration. Plus KOH, leaving a space in case I need a coefficient in there. And then what are my products going to be? We're going to get potassium sulfate and water. One of the products is always water, and the order in which you write them doesn't matter. 1 plus 2 or 2 plus 1 is the same thing. So if you want to write the water first, that's fine. If you want to write the other one first, that's fine. So this potassium and the sulfate are going to combine together. You have to get the correct chemical formulas here. That's going to be K2SO4 because sulfate has a -2 charge and potassium has a +1 charge. And then we need to balance this. Over here, K2, there's 2 potassiums, so I need a 2 over here. And I have 1 sulfate and 1 sulfate. I've got 2 hydrogen ions and 2 hydroxide ions. That's going to make 2 water molecules. You can also balance it by looking at individual elements. It takes a little longer, but slow and steady always wins the race. Okay, any questions about that? Now let's take these numbers and write them under the equation. This comes out to be a volume stoichiometry problem. So 20 milliliters of sulfuric acid. So 20 milliliters of the H2SO4. And we have 22.87 milliliters of the potassium hydroxide. And we're also given the concentration. And capital M is moles per liter. And we're trying to find the concentration, moles per liter, of that one. Now, there's different ways to approach this. And I never think ahead to decide which way I want to do it. The problem I'm anticipating is we've got liters down here, and we have milliliters here. And we're going to have to deal with those somewhere. One approach is to convert your volumes to liters and be done with it. Another approach is that we can use a unit called millimoles. So 0.158 moles is the same as 0.158 millimoles per milliliter. And that works also. I think what we'll do here is we're just going to convert. I'll save that for later. So 20 milliliters is how many liters? 0.02. 0.02 milliliters. I want to keep my sig figs. And then 22.87 0.87 is 0.02287. Now, that's not magic that I'm doing. 22.87 milliliters times liters over milliliters. This will be 10 to the minus 3. And you can do the math and prove to yourself that that's what we get. We convert milliliters to liters a lot in 1A, and what we're doing is we're dividing by 1,000. We're moving the decimal point over 3 places to the left. So however you get there, our end result should be the same. What do we need? Oops, I didn't mean to do that. What do we need to find the moles per liter for the sulfuric acid? We need moles and we need liters, right? So we need to take the moles of sulfuric acid and divide by the liters. This is the volume right here. So what we need is we need to find the number of moles of sulfuric acid that were present. So our path is going to be liters of KOH to moles of KOH to moles of H2SO4. That's the stoichiometry part. Once we get this, we know the volume and we can divide it and find the concentration. So I have 0.02287 liters of KOH. And I'm going to go to moles of KOH and then moles of H2SO4. So I've got liters down here, liters of KOH, and those units are going to cancel out. And down here I've got moles of KOH, and these units are going to cancel out. So this is the molarity of the solution, which they gave us, 0.158. And this is from the balanced chemical equation. There's 2 moles of KOH. Just throw the calculator around. They like that. That's probably why my last one quit working. 0.2287 times 0.158 divided by 2. So I get a number of moles that's 0.001800673 moles of sulfuric acid. How many significant figures does that number have? Well, how many should it have? Wrong question. 3. This number has 4. This number has 3. So this really has 3 significant digits. The rest of them are extras. I don't want to throw them away yet, though. So now the molarity is going to equal that number, 0.001800673 moles, divided by the volume in liters, 0.0200 liters. That number is still in my calculator. I'm just going to divide by 0.02. And I come up with 0.09. This is my final answer, so I'm going to round it 3 significant figures. Moles per liter, or 0.903 capital M. Any questions? couple of you look worried. It's okay. Now I'm going to warn you about something. Sometimes students like to use the dilution equation to do titration calculations. M1V1 equals M2V2. And what's really tricky about that is it works sometimes, but not all the time. It will not work on this problem. Using the dilution equation for a titration is not a good idea. It ignores the stoichiometry of the reaction. This is not one-to-one. And so I think it's a very dangerous thing to do it that way. Okay? I think it's better to understand what's going on. We're not just adding water to something. We have a chemical reaction occurring. Chemical reactions, we use stoichiometry. So we've got liters to moles, and then we're going to divide by the volume, and we get the molarity. Any questions? Gas evolution reactions. So sometimes gases form when you have a chemical reaction. Sometimes they form directly. This is an example, bless you. Potassium sulfide reacting with sulfuric acid will generate aqueous potassium sulfate and dihydrogen sulfide gas. It smells really bad. This is a direct product, and it's a gas. Others form gas because one of the products formed in an ion exchange reaction actually decomposes. So if you mix sodium hydrogen carbonate, baking soda, with acid of any kind, you could try that at home. You've probably noticed this. If you mix baking soda and vinegar, what happens? It bubbles and fizzes, right? If you've ever made a volcano in school, that's probably what you used. Well, when we look at what happens when these ions change places, we get sodium chloride, which is salt, and we get H2CO3, carbonic acid. But carbonic acid is unstable, and it decomposes into water and carbon dioxide, and there's the gas that we see bubbling out. Here's a picture of this actual photograph of what's going on, and then diagrams showing the process with the little particles. So carbon dioxide is formed. It forms as a gas. Those guys kind of hang out together, and the little bubbles come up to the surface and pop and go away. So these are the gases that will form. These are the ones you need to know about. Okay? So if you get a reaction that produces H2S, that's going to be a gas. That's its physical state, and you need to write it as such. And there's an example reaction. The other three, these are gases that form from intermediate products. So if you get carbonic acid, if you get sulfurous acid, or ammonium hydroxide, when you swap the partners in your reaction, you need to remember that those are unstable. So let's look at these guys, because it's really not that bad. So H2CO3. So that's going to be unstable. And water is one of the products that comes out of all of these. So we've got water, and then if we pull a water molecule out of H2CO3, we lose both the hydrogens and one of the oxygens. What's left? CO2. That's carbon dioxide. That's a gas. Let's look at sulfurous acid. H2SO3. That's also going to split into water and something else. Well, if we take 2 hydrogens and an oxygen away from H2SO3, we get SO2. And you need to remember that that is a gas. That also doesn't smell good. Most things that have sulfur in them do not smell good. NH4OH will also decompose to water and something else. Well, what's left when we take away 2 hydrogens and an oxygen? NH3. Ammonia is a gas at room temperature. Ammonia also doesn't smell very good. That'll clear your sinuses out real fast. Won't make you happy, though. Any questions? So if you see H2S or these guys as your product, you have to remember to go ahead and decompose those guys into gases. Okay, so write a molecular equation for the gas evolution reaction. Oh, the typos. That occurs when you mix aqueous hydrobromic acid and aqueous potassium sulfite. Well, what's the formula for hydrobromic acid? HBr. The prefix hydro tells us that this is a binary acid, not an oxyacid. So the bromic, it's bromine and hydrogen. This is asking us for an equation, and so it's a good idea to put the state symbols on there. Again, on a test or on a lab, if you're not specifically told to include state symbols, I won't get on you about it, but it's a good idea, especially when they're giving you words like aqueous in the question. And potassium sulfite. K2SO3, so that's potassium and sulfite, and we put those together and we get K2SO3, and that's also aqueous. So what's the product of this reaction going to be? Well, let's look at the ions. Hydrobromic acid forms hydrogen ions and bromide ions in solution. Swapping partners. Okay, so the K and the Br go together, and the H plus and the SO3 minus go together. So I'm just going to write them over here. H plus, SO3, 2 minus, and potassium and bromide. So let's put this together. This is H2SO3. Is that going to be soluble, do you think? It is. How about KBr? Soluble or insoluble? Soluble. Potassium. All potassium things are soluble. And this, when you see this guy, your brain should go ding, ding, ding. That's one of those guys. Decomposes. So I'm going to clear this out. We're going to have a lot of scribbling in here, and then we'll write it all nice and neat at the end. What does this decompose into? Water and what's left. The water would be a liquid, and what's left is SO2, and that will be a gas. Now, this is a big old mess, isn't it? HBr aqueous plus K2SO3 aqueous forms H2O liquid plus SO2 gas plus KBr aqueous. Because if we just form two aqueous products, there's no reaction occurring. But there is a reaction here because what we really end up with is a gas and a liquid. Those are two new substances. Are we done? No, it's not balanced, is it? Well, let's look through this. There's one hydrogen here. There's two over here. So I'll put a 2 there. And bromines now, there's 2 BRs here, and there's only one on the right side, so I'll put a 2 there. Potassiums, there's 2 and 2. SO3. Now, the SO3 came apart, didn't it? So we can't balance sulfite as a unit. So I have to look at the sulfur and the oxygen separately. Here's sulfur, 1 and 1 sulfur. Here's 3 oxygens. There's 1 oxygen in the water and 2 in the sulfur dioxide, and so there we go. Any questions?